Welcome to question 2 from the 2019 ELEC1 paper. Okay, so for part A, the question states simplify the following Boolean expression using the rules of Boolean algebra. Okay, so we've got our expression. First thing we need to do is expand the brackets. So what this should look like is this. So Q is equal to A and not A, or A and B. Now what you need to do is use our Boolean identities. And hopefully you should recognize that A and not A is equal to 0. So now we have 0 or A and B. And again, we use our identities and recognize that 0 or A and B gives us an answer of A and B. Okay, to the second part of the question, part B. So write down the unsimplified Boolean expression linking the output Q of the following topic system to the inputs A, B, and C. Now it does say unsimplified, therefore all we need to do is just use the particular lines in our information here in order to get our outputs. So let's just go back, and what we need to do is recognize those particular outputs which are high and the lines that go with them. So we're looking at this particular line here, and we're going to also look at this line here and this line here, and these are the only three parts that we need in order to give us our answer. So it's unsimplified. So for the first part of the expression, it's not C and not B and not A. The second line would be not C and B and not A. And the last part would be C and not B and A, where we're putting the nots where the inputs C, B, or A are low, and we're putting the normal parts for when they're high, and we're linking them using the OR gate expression. Okay, so part C, we've got a Karnaugh map. And so, in order to get all the marks, it says simplify the Boolean expression using a Karnaugh map. Right, so first thing we need to do is populate the Karnaugh map. So not D and not C and B and not A. So not D and not C is this top line, and B and not A gives us a high in the top right hand corner. Then we have D and not C and B and not A. So we're looking for 1 0 1 0. So we have a high in the bottom right hand corner. Then we've got not D and C and not B and not A. So we're looking for 0 1 and a 0 1. So we're looking for a high here. Then we've got D and C and not B and A. And therefore we're looking for a high here. And lastly, we don't have a D in our last expression, so D doesn't matter, it can be both high and low. And we had C and not B and not A, so we're looking for C to be high and B and A to be low, and we have these two boxes. Now in order to get marks, the full marks for Eduqas paper, we need to label the Karnaugh diagram before we actually give the final expression. So we know we have a group here, and we have a pair here. So now we need to label them. So this group, D is both high and low for the pair, but C is low, so we know we're going to have a not C. And because they're in the column where B is high and A is low, we have basically not C and B and not A for that particular part. And then for the group of 4, D can be both high and low, and A can be both high and low, but C is high and B is low. So this is C and not B, which gives us a final answer of C and not B, or not C and B and not A. Okay, so on to the 6 marker at the end. Now, the first thing we need to do is to actually recognize what we have here in terms of a circuit. Things to recognize is that you've got an OR gate on the right hand side, and that OR gate means that any high input into that OR gate, then the LED will be on. Everything else we need to actually work through the particular question to see exactly what it means. So the question says the logic system shown below has been designed to satisfy the following specification. When neither switch is closed, the LED is on continuously. When neither switch is closed. So what they're really saying is when either or both switches are open, the LED is on continuously. Okay, right. When either switch is closed, but not both, the LED flashes at a frequency of 1 Hertz. When both switches are closed, the LED flashes at a frequency of 2 Hertz. Okay, so there's a difference in those two frequencies. The switch units output a logic 1 signal when closed. The LED requires an input signal of logic 1 to make it light. And it says evaluate the logic system against the specification and suggest improvements. So we've got 2 things really we need to do there. We need to evaluate and then we need to do improvements. Okay, so before we start with this though, we need to remember these particular truth tables. NAND gate, only when you have both inputs high is the output low. Exclusive OR, if either of the inputs are high but not both, then the output is high. And a 3-input AND gate, similar to a 2-input AND gate, only when all of the inputs are high is the output high. Now, the way to tackle this question is to think about those 3 gates on the left-hand side, the NAND gate, the exclusive OR gate, and the AND gate. And we'll look at the 3 conditions to see whether the specifications met for each of them. All right, so let's have a look at the first one. It says when neither switch is closed, the LED is on continuously. So that means when both switches are open, the LED is on continuously. Well, the output for a NAND gate, when you've got 2 lows going into it, is a high. For an exclusive OR gate, it's a low. And for an AND gate, it's a low. Now, that high from the NAND gate is going to go into a 3-input OR gate, which means the output will be high, which means the LED will be on. So is the specification met? Yes. Okay, so let's look at the next one. NAND gate. Well, if either of the inputs are high, then the output for a NAND gate is high. Okay, so let's just do that again. There we go. Exclusive OR gate. Well, the output for an exclusive OR gate is going to be high. And then because of the pulse generator connected to the 2-input AND gate, what you're going to get is ultimately the output of AND gate is going to be 2 Hertz. And then the AND gate at the bottom is going to be a low because you need both inputs to be high. Does this meet the specification? Well, the specification is when either switch is closed but not both, the LED flashes at a frequency of 1 Hertz. Well, the NAND gate on its own would suggest that the LED is high all the time. So is this specification met? No. But we also need to make a note that the output from the 2-input AND gate is going to be 2 Hertz, not the 1 Hertz that's required by the specification. That's something we're going to come back to. And then finally, we go to the last condition. When both switches are closed, the LED flashes at 2 Hertz. Well, The output from the NAND gate is going to be a low because both inputs are high. The output from the exclusive OR gate is going to be a low because you need either but not both inputs to be high for the exclusive OR gate to have a high output. But the 3-input AND gate at the bottom, well, the conditions met for 2 of the inputs, because we've got switch A and switch B both giving a high into the AND gate, and the pulsing generator will have highs and lows. So when the pulse is high, the output to the 3-input AND gate will be high, and when it's low, it'll be low. So we will get a 2 Hertz pulsing output. From the AND gate. Well, does that mean that the specification is met? Yes. So we know that condition 1 and condition 3 are met, but not condition 2. So what improvements do we need to make? Well, there are 2 improvements. The first one is that fact that that NAND gate gives a high when either of the inputs are high. And what we want is that to be removed. Now, the only way to do that is to replace that NAND gate with a NOR gate. So we're just going to put that as our first answer. And now we've got to solve the problem of the 1 Hertz output rather than 2 Hertz. Now, there's 2 ways of doing this. The first way you could do it, if you wanted to, is detach 2 Hertz input from 2-input AND gate and link instead to 1 Hertz pulsing input, which means that we'd actually have 2 pulse generators, one at 2 Hertz going into the 3-input AND gate and one at 1 Hertz going into the 2-input AND gate. More eloquent though is probably this one. On the input to the 2-input AND gate, attach a divide by 2 D-type. Now, I think that's more eloquent, but the choice is ultimately yours. For me, I would probably draw it as well, and my final solution would look like this. Okay, that's the end of question 2.